Hello everyone, this is my English speaking practice and I'm working on coding problems. My throat still hurt a bit, but I'm going to stream my programming. Today's first problem is cheapest flights within K-stops. There are n cities connected by some number of flights. You are given an array flights where flights I equal from to price. Indicate that there is a flight from city from to city to with cost price I. You are also given three integers source, dist, and k. Return the cheapest price from source to dist with at most k stops. If there is no such route, return -1. Let's take a look at example 1. Input n is 4, so there's four cities. Flights is 1, 2, 3, 4, 5. 5 flights. And we want to go from source 0 to city 3 and case 1. So we have to return the cheapest price from source to dist within at most 1 stops. Okay, so in this case we have one option 0, 1, 3. Okay, so the answer is 700. The graph is shown above. The optimal path within at most 1 stops from city 0 to 3 is marked in the red and has cost 100 plus 600 equal to 700. Note that the path through cities 0, 1, 2, 3 is cheaper, but it's invalid because it uses 2 stops. 0, 1, 2, 3. Makes sense. Okay. Yes. And constraints. The cities are 100 at the most. And there will not be any multiple flights between 2 cities. Okay, got it. So basically I'm gonna do BFS to find the path to the source to destination, and while doing that I'm also validate the cost because validate the number of stops because we are given k. We are limited to stop at the most k stops, so we have to keep track of the number of stops while doing BFS breadth first search, and and we have to check all possibilities because we might update the cost to reach the destinations. Okay, makes sense. So let's think about the data structures. Data structures is like queue of tuples. And the tuples is node, that is city in other words, and city and cost and stops. Yeah, maybe we have to keep track of these three informations, and basically we're gonna do the BFS, and if the number of stops is more than k, we cannot use the path. Yeah, we can no longer use the path, so we don't move on to the next for the path. And if the city is a destination, we can update the cost to reach the destination if it's the smaller, cheaper cost, right? Yeah. I think this works. So let's think about time complexity. Time complexity, it would be O of n, and where n is the length of flights, because we have to check all of edges, all of flights. So yeah, the BFS takes all of n, right? Yep. And the space complexity, we already have flights, that's the important information, and we're gonna use it. And yeah, we have to prepare queue for BFS, but the length of queue is up to the length of flights, so the space complexity would be the n, where n is the length of flights. So O of n and O of m, that's complexity. Okay, let's start to code. I forget the deque in Python. Yeah, it's like this. Okay. Okay, so first we prepare the queue and initialize the state. It's gonna be source. And how to identify the source information? Yeah, so append city source, and the number of stops should be 0 at first, and cost is also 0 at first. This is the first state, and while Q have a element, we are gonna move on to the next, so we can retrieve information from the queue that is pop left. The queue is a data structure like first in first out, so we can get information from the queue through pop left and city stops cost. But if city is destination, we can get to the destination, so the answer would be we want to return the cheapest price, so the answer answer might be updated, and we how about this? If we when we get to the destination, we don't need to explore more, because the cost must be the minimum. Cost must be minimum, so we cannot achieve the cheaper cost from this state. So if they are the same, we just check the cost and finish exploring from this state, from this path. And otherwise, we also have to check the number of stops might be more than k. It's invalid, so we do nothing anymore. Just continue, just look at the next. Okay. And otherwise, we need to explore the next from this state, so means from to price. Okay, from to price. Okay. Or maybe we have to construct build because we want to use the city as a key, but this data structure doesn't have a key. So for example, this one and city 1 have a two flights. So yeah, so I mean the graph is like city 1 have a no, city 1 have a list and it should have destination and cost like this. Yeah, so the price, source and destination. So graph at source would be destination and cost, right? And okay, wait. I also have to manage the minimum cost to reach the city. Because it have a cycle, so for example 0 to 1, 1 to 2 and 2 to 0, right? And 0 is already visited but might be updated because it can be reached with minimum cost, smaller, more cheaper cost. So I see. So the cities is represents the list of prices, list of minimum prices to get the city. So it is it is initialized like this. And this source, that is a first place, so the cost is 0, right? So if we can visit the city, we check the cost. We can update a cheaper one, right? We can update a cheaper one, and okay, come back to the exploring next state. So we can get flights from the city and that have destination and cost. And the cost, this means the current cost, it's accumulated. So the next cost is cost plus this flight's cost. That is the next cost. And stops, yeah, we have to increment the stops, number of stops. So the information is like destination and stops plus 1 and next cost. But it we have to check if the next cost is cheaper than the current cost to visit the city that is we are gonna going to. Because we already visited with a cheaper price, we don't need to explore the next because it cannot contribute the answer. Right? So this is important condition. So in this case, the zero is a source, so it means we already visited with cost 0 and we process the search and we reach to 1 and we reach to 2 and we have 2 options and we try to explore the next state for this flight, but 0 is already visited and the cost is 0 and we are going to try to go to 0 with cost 300, but we don't need to because we already visited. Yeah, so this is that condition. Yes, looks good. So the answer is minus 1 if the answer equal to infinity, because answer might be updated, might not be updated. The city, once city same to is equal is once city equal to destination, we can update the cost. It must be less than infinity, yeah. But there is a possibility to be not able to reach the destination. In that case, answer still remains infinity, so we return minus 1. Yeah. Flights. Wrong answer. What is wrong? Stops 2. Oh yeah. Oh yeah. Stops 2. Stops 1. Ah, I see. Oh wait. in this case, great. But I'm thinking about the number of stops. This condition is good. It's okay. I was thinking about the condition for the minimum cost to visit the city. Yeah, I'm thinking about I should take the number of stops into consideration when we update the minimum cost to visit the city. Yeah. Because if it because that is not always optimal. That is not always optimal to store the minimum cost, because it takes more cost, but it can visit with less number of stops. But I figured out this is the BFS, so stops is basically increase one by one. So when we update cities, the stops is when we update the cities twice or third times or fourth times, or yeah, when we update the cities later, the number of stops must be greater or equal to the ones that is used when the city is updated at first. So we don't think about the number of stops, I think. Yeah, if the cost is cheaper, that is best. So I will go with this, but there are any edge cases? I'm not sure. Let me see the result. Cool. Cool. Nice. Nicely done. Let me see. Complexity. E is the number of flights and V is the number of cities. The reason for this is that the outer while loop runs when information's away. Oh, this is a little bit complicated, I think. My answer is so smart. This is same. This is same. I see. So, where E is the number of flights, V is the number of cities. What is a K? The reason for this is that outer while loop runs at most V iterations. V iterations. And in each iteration, the inner while loop runs for the most E iteration. However, the maximum number of times and can be processed is limited by K. Yeah, I think this is correct because this is this and E plus E. I think E plus E. Oh, that's... What is this? Anyway, my solution is correct, so let's move on to next. All paths from source to target given a directed acyclic graph DAG of n nodes labeled from 0 to n minus 1. Find all possible paths from node 0 to node minus 1 and return them in any order. The graph is given as follows. Graph I is a list of all nodes. You can visit from node I. There is a directed edges from node I to node graph ij. Makes sense. Okay. So the graph is like this. We have to return all possible paths to 0 to 4. 1, 2, 3, 4. 1 1 2 3 4 1 2 3 4 5 wait 1 2 3 4 5 makes sense. This is different type of problem. N is not too large. My first, the idea that comes to my mind first is to use DFS, and I don't think we can assume there is no cycle. Because there is cycle. If there is cycle, we can generate infinite paths, because 0 1 3 0 1 3 0 1 3 and 4 and 0 1 3 4, that's a different path. So let me assume there is no cycle. So in this case, we just use DFS and start at 0 and 1 3 4 and 4. When it reaches the target node, that is the answer, and finish exploring its path. And when we reach to 1, we have 4, can reach 4 3 and 2 yeah. So basically DFS can go every edges, so it would be the answer. Yeah. The time complexity is n is number of edges. I don't know the number of edges, but n is uh, it's n squared, where n is the number of nodes. That is the number of edges at most. N squared. So n is here is a base case, and we backtrack here. Let me see. That doesn't improve. Yes. What is wrong? Pen 0. What's wrong? Print percent node. Oh, n minus 1. No. 0, 1, 2, 3. N minus 1. Yeah, minus 1. Correct. Is there any edge cases? Graph length is n. If there is a cycle, I think that doesn't make sense as a problem, so yeah, I can assume there is no cycle and this DFS will finish. So let's submit it. Great. This is easy one. So find eventual safe states. Let's go. There is a directed graph of n nodes with each node labeled from 0 to n minus 1. The graph is represented by 0 indexed to the integer array graph, where graph I is an integer array of nodes adjacent to node I, meaning there is an edge from node I to each node in graph I. A node is a terminal node if there is no outgoing edges. A node is a safety node if every possible path starting from that node leads to a terminal node or another safe node. Return an array containing all the safe nodes. The graph, the answer should be sorted in ascending order. Okay. So graph is like this. 0 is connected to 1 and 2. Yes. 1 is 2 and 3. 2 is going to 5. 3 doesn't have outgoing path. 4 is to go. 4 is going to 5. 5 and 6 is also a terminal node. So there is 3 is connected to 0. So we have 2 terminal nodes. And safe nodes. The safe node definition is every possible path starting from that node leads to a terminal node. Two is good. 4 is good. 5 is terminal node itself. 6 is also. The given graph is shown above. Node 4, 5, and 6 are terminal nodes as there are no outgoing edges from either of them. Every path starting at node 2, 4, 5, and 6 all leads to either node 5 or 6. How about 0? 0 is connected to 2 and 2 is connected to 5. I didn't understand. I don't understand. or another safe node. So I interpreted that the node 0 is connected to a safe node 2 because 2 is to have a path to the terminal node, so 2 is a safe node, so 0 is also have a path to the another safe node, right? Am I wrong? A node is a safe node if every possible path starting from that node leads to a terminal node. Yeah, this is my question. Shouldn't 0 and 1 also be included in the answer? I was wondering about this too. This should have been clearly mentioned in the question. I had to look at the replies to find out why. Yeah. I think the key here is must work to our terminal node. 0 can go. I understand. Every possible path from starting from, so 0 have two paths, 2 and 1, and 2 is one of the paths lead to the terminal node, but this path is infinite and it doesn't lead to the terminal node. Okay, makes sense. Every possible path starting from that node leads to the terminal. Makes sense. So what is the question? Return an array containing all the safe nodes of the graph. I see. That's interesting. Or possible paths. So infinite loop is obviously not good. Okay. So in other words, when we use a DFS, the answer node when we use DFS from the answer node, it must be end, and otherwise For example, when we start DFS at 0, we have two options, and in this path can finish exploring, but in this path is has a loop, so it's invalid. We can find out. And how about this? One. It's I already get to know because we explore 0 and 1 and 2 and 3 and 4 already explored these nodes, and 0 and 1 and 3 are included in infinite cycle. So we can find out 0 and 1 and 3 are not good, and also get to know 2 and 5 is good because it's lead to terminal node. So we can skip 1, 2, and 3. We start at 4, and 4 is just one path, so 4 is also the answer, and 6 is also answer. Yes, so we are going to DFS, and we have to explore all edges. So the time complexity would be number of edges. And the space complexity, we want to use list to keep track of the flag. That is for the node is included in a cycle or not. If it's not in a cycle, it must be leads to the terminal node, because it's terminated eventually. So that must be one of the answers. So the space complexity would be the n, where n is the number of nodes. So basically, the list of booleans is true. It might be answer, and it times n, it have n elements, and no, let me initialize with 0 and 0 and 1 and 2. Not visited. Okay. So I in range n, and if if it's not visited, we have to execute the DFS. This function basically update to the answers. So maybe it should have path and I use the backtracking, so start with I and and the node is the terminal node. This means there is no outgoing edges, so yeah, so this path this path could be answer, but the yeah, but all of elements always are the answer, not always the answer, because 0 to 5 is the one valid path, but 0 is have another path like this, so 0 is not the answer. So yeah, we cannot find out from this path 0 to 5 and 0 is good or not. So outgoing path. So how about return the valid nodes? Because we are going to loop through neighbors, and Neighbors. It returns good or not. And if invalid is empty, we can append what's happened? What happened here? What happened here? we have two paths, 0, 2, 5 and 0, 1, 3, 0, 1, 3, 0, 1, 3. So at this point we call to DFS, and this case returns 2 and 5. So this case returns true because the 5 is the terminal node, and at this point this also returns true because this has one outgoing path and it returns true, so all true, so we can return true. So that means we don't need to we just want Boolean that is if B is true, we can update answers nay equal to 2. Otherwise, answers nay equal 1. Okay. And also append the Boolean value to the checks. So there is one false result. The flag becomes false and return flag. Makes sense. And yeah, here is a base case. So this means the node is graph node. Graph node is the terminal node. Graph node is a terminal node. So can return true. And we have to find the cycle. So and also Oh wait. Mm. Mm. Yep. I think let me see. Runtime error checks. Mm. 4 and 6. Hmm? Oh wait. If one if the if it connect to the not good node, it's it have a bad path, so the flag would be false. Otherwise, yeah. Otherwise, flag keeps true. But what is I see. When return true, we have to update. So I mean right? Right. And when return true, we update it to 2. Return false, update it to 1. Correct. Let me see. Great. Nice. So nice. So let me see. Let me explain this code. I'd like to write a comment. So there is a directed graph of n nodes with each node labeled from 0 to n-1. The graph is represented by 0 index to the integer array graph, where graph I is an integer array of n nodes adjacent to node I, meaning there is an edge from node I to each node in graph I. A node is a terminal node if there are no outgoing edges. A node is a safe node if every possible path starting from that node leads to a terminal node or another safe node. Return an array containing all the safe nodes of the graph. The answer should be sorted in ascending order. So, so the key thing here is when we use DFS, it basically finish exploring like 0 to 5 because it's because the 5 is a terminal node, meaning that doesn't have any outgoing path. So that's we call that's a good path. Okay, and on the other hand, the DFS never finishes sometimes. For example, 0, 1, 3, and 3 have a path to the zeros, so it have a loop. Okay, so the DFS never finishes, and we call it bad path. Okay, so the node that consists of that are included in a bad path, that never be the answer, that never be the safe nodes, because the safe nodes should have how to say, the safe node should have paths such that all of them lead to the terminal node. Okay, so once we find out the node is included in the cycles, the node is not good. So this is a key concept. Okay, so we basically do the DFS and to keep track of information for each node. 0 is not visited and 1 is the node is included in cycle path, and so the node is not the answer. And the 2, that means every possible path leads to our terminal node. So in other words, the connected to safe node or terminal node, right? So based on this, we implement DFS. And these two condition is the base case. Let me write a comment. Node is a terminal node, so the outgoing path is 0. So we can update the answers array to 2 because it's a terminal node itself, and also return true. Yeah, the returning Boolean value is important because it is used to check if the node is check if the path is good or not. Okay, so this function returns true because it leads to a terminal. Okay, and this is base case. Another base case, node is included in cycle path. So this function takes path, and that is a set data structure, and it have a node, collection of node we already visited. If it's in the path, it have a cycle. We can find out there is a cycle. So this node is included in the cycle. So the answer would be 1, and yeah, this is never updated. Yeah, we can fix the information about this node and return false because that's not a good node. And here is a normal case. Update path and flag is true. Flag is true. Flag is node is good initially, and we have to check if all every possible paths are good or not, right? And if the neighbor node is not visited yet, we need to explore the node and find out the node is need to find out that the node is safe node or terminal node. Condition is every path, so we use AND condition here, and this is about unvisited node, and if this node is connected to the invalid node, so that means answers is 1. Right, okay, and when the answer is 2, that means the neighbor node is a good node, lead to the terminal, so we don't need to anything here because the flag is true. If the flag is true. Yep. And we basically do this about unvisited node. So yeah, the condition is like this, and finally we have answers. So if its value is 2, that is a valid node, so we append it to the list and return it. Okay, so it's time to have it reviewed. Not visited yet, included in a cycle path, leads to a terminal node. safe node or terminal node. Base case, this node is a terminal node. Base case, this node is part of a cycle. Normal case, add the current node to the current path. Flag represents whether this node is safe or not. We assume it's safe initially. We need to check if all paths from this node are safe. If the neighbor node has not been visited yet, we need to explore it and find out whether it's safe or terminal. Since the combination is every path must be safe, we use AND. If this node connects to the unsafe node part of a cycle, that means this node also have a path that never leads to a terminal node. If flag is true, it means all paths from this node leads to terminal nodes. Otherwise, this node is not safe. Not visited yet. A cycle path. Node is a terminal node. Neighbor node is not visited yet. Has not been visited yet. We need to explore the node and find out whether it's safe or a terminal. Okay. The current node also have a path. This node also have a path. All paths from this node leads to terminal nodes. But my original sentences make sense, I think. Okay, so I solved 3 problems today, so yeah. I'm getting better at graph problems, so from tomorrow I wanna take problems randomly, so I think around this. The recent problem is listening English. Yep. But anyway, I also needed to practice speaking, so yeah, I will do it tomorrow. See you.